texture filtering, the hidden performance cost in every Unity project. Hello and welcome to episode number 15 of the Unity Performance Task Force podcast. I'm your host, Ruben from TheGameDev.Guru, and as usual, I'll kick things off with a question for you. Have you ever wondered why some games look crisp and smooth while others feel blocky or shimmery, especially when surfaces tilt away from the camera? The answer is texture filtering, and it's costing you GPU cycles in every single frame. Sounds familiar? If so, this episode is for you. Here's the thing. 99% of Unity projects use textures, whether you're doing 2D casual games, AAA 3D titles, or VR experiences, you're painting data onto surfaces. Albedo textures, normal maps, height maps, they're all just arrays of texels, collections of bytes that the GPU reads and samples thousands of times per frame. But here's the problem. Your textures are static. They sit in memory with a fixed resolution and a fixed layout. Meanwhile, the 3D surfaces you project them onto, they're constantly changing. Players move the camera, objects rotate and scale, screen resolutions vary. Suddenly, there's no clean one-to-one mapping between a screen pixel and a texel in your texture. So which texel should the GPU pick? That's the core question texture filtering answers. Let me paint a picture. Imagine you're looking at a traffic light far in the distance. That traffic light has a detailed texture, maybe 512 by 512 pixels. But on your screen, that whole object is just 1 pixel wide. Which of those 262,000 texels should you sample? Do you grab the top left corner, the center, some average? Or flip the scenario. You're standing right next to a wall with a low-res texture. Now one texel needs to cover dozens of screen pixels. Do you just stretch it and get blocky artifacts, or do you blend neighboring texels to smooth things out? This is not a theoretical problem. This happens constantly. Every fragment shader, every draw call, every surface with a material is asking the GPU to figure out this mapping. And the strategy you choose, point filtering versus bilinear versus trilinear versus anisotropic, that choice has direct performance implications. Let's break down the options. First, point filtering, also called nearest neighbor sampling. The GPU calculates where your screen pixel lands in texture space, which is continuous, not discrete. Then it just snaps to the closest texel and uses that color. Simple, fast. But it gives you that classic blocky, pixelated look. Texels pop in and out as you move. It's fine for retro aesthetics or very specific art styles, but for most projects, it's not acceptable visually. Second, bilinear filtering. Instead of picking one texel, the GPU samples the 4 nearest texels around the projected pixel location and calculates a weighted average. This smooths out the blockiness. You get nice gradients between texels. The cost? 4 texture samples instead of 1. But here's the kicker. Modern GPUs are built to do this efficiently. Bilinear filtering is almost always the baseline you should assume. Now, both point and bilinear work well when the surface is roughly perpendicular to the camera and the texel to pixel ratio is close to 1:1. But what happens when you zoom out? Or when surfaces tilt at steep angles? That's where mipmaps come in. Mipmaps are pre-calculated downsampled versions of your texture. The original texture is MIP level 0. Then you generate MIP level 1 at half resolution, MIP level 2 at quarter resolution, and so on, all the way down to a single pixel. Unity generates these automatically unless you disable mipmaps in the import settings. Why do mipmaps matter? Because when a surface is far away or tilted, you don't want to sample from the full resolution texture. You want to sample from a smaller MIP level that better matches the screen space resolution. This reduces aliasing, those shimmering artifacts you see on distant surfaces. It also improves GPU cache performance because smaller textures fit better in the texture cache. But here's the new problem. As the camera moves, the ideal MIP level changes gradually. If you just snap from MIP 0 to MIP 1, you'll see a visible pop. the surface suddenly gets blurrier. Enter trilinear filtering. Trilinear samples from two adjacent MIP levels and blends the results. So if you're between MIP 0 and MIP 1, the GPU samples 4 texels from MIP 0, 4 texels from MIP 1, and then blends those two bilinear results together. That's 8 texture samples per fragment. The transitions between MIP levels become smooth. No more popping. The cost? Roughly double the texture bandwidth of bilinear, though in practice it's not always a full 2x hit because of caching. So far so good. Trilinear filtering handles zoom and distance beautifully. But what about angles? Picture a floor stretching out in front of you. The floor tiles close to the camera are nearly 1-to-1 with screen pixels, but the tiles far away, near the horizon, are tilted at a steep angle. Each screen pixel now covers a long, narrow strip of texels. Trilinear filtering samples in a square pattern, so it doesn't capture that anisotropy, that directional stretching. You get blur. That's where anisotropic filtering comes in. Anisotropic filtering takes multiple samples along the direction of maximum stretching. Instead of a square footprint, it uses an elongated footprint that matches the angle of the surface. The result? Sharp, clear textures even on surfaces tilted away from the camera. Unity lets you set anisotropic filtering per texture or globally in quality settings. The parameter is the sample count: 2x, 4x, 8x, 16x. Higher numbers mean more samples, sharper visuals, and higher costs. But here's the good news. Modern GPUs handle anisotropic filtering surprisingly well. The cost is not linear. 16x anisotropic is not 16 times slower than 1x. It's more like 10 to 30% slower in texture-heavy scenes, depending on your hardware and how many surfaces are at steep angles. So what's the performance cost in practice? Point filtering is the fastest, but visually unacceptable for most projects. Bilinear is the standard baseline. Trilinear adds some cost, but it's usually worth it to avoid MIP popping. Anisotropic filtering adds more cost, and this is where you need to make a decision based on your target hardware. For high-end PC and console games, 16x anisotropic is often free in terms of user-perceived performance. The visual improvement is massive, and the frame time cost is negligible. For mid-range mobile, you might dial it back to 4x or 8x. For low-end mobile, especially older devices, you might disable anisotropic entirely and stick with trilinear or even bilinear. Here's the decision tree I use at TheGameDev.Guru when we audit projects. First, confirm MIP maps are enabled on all textures unless you have a specific reason to disable them, like UI textures that never scale. Second, set the default filtering mode to bilinear in your texture import settings. This is the minimum acceptable quality for 3D surfaces. Third, enable trilinear filtering globally or per texture if you see MIP popping during gameplay. This is especially important for surfaces that change distance frequently, like terrain or large environment props. Fourth, test anisotropic filtering on your target hardware. Start with 4x. If your frame time budget allows, go to 8x or 16x. If you're struggling to hit 60 FPS on mobile, dial it back to 2x or disable it entirely. Profile in the real world on real devices, not just in the editor. Fifth, check your texture resolution. If you're using 4K textures on a mobile game, anisotropic filtering is the least of your problems. Downscale your textures first. Filtering mode is a multiplier on texture cost, but resolution is the base cost. Get the base cost under control before you optimize the multiplier. Now let's talk about common objections. Objection 1. I enabled 16x anisotropic and my frame rate tanked. If that's true, you're likely GPU bound on texture sampling, which means your textures are too large, you're sampling too many textures per material, or your target hardware is very weak. The fix is not to disable anisotropic filtering. The fix is to reduce texture resolution, combine texture maps, or optimize your shaders to sample fewer textures. Anisotropic filtering is a symptom amplifier, not the root cause. Objection 2. I don't see any difference between bilinear and trilinear. Then your surfaces aren't changing distance enough to trigger MIP transitions, or your MIP maps are disabled. Test by zooming in and out on a textured surface. If you see sharp transitions where the texture suddenly gets blurrier, that's MIP popping. Trilinear fixes that. Objection 3. Anisotropic filtering makes everything look worse on my floor texture. That's unusual. Anisotropic filtering should make floors and walls look sharper. If it's making things worse, check your mipmap settings. If mipmaps are broken or if you're using a poorly generated mipmap chain, anisotropic filtering will amplify those issues. Regenerate your mipmaps or re-import the texture. Alright, here's your action plan. Step 1. Open your Unity project and check your quality settings. Set the anisotropic filtering mode to forced on or per texture. Start with 4x globally and profile. Step 2. Go through your most expensive materials, the ones used on large surfaces like terrain, floors, or skyboxes. Make sure those textures have trilinear or anisotropic filtering enabled. Use the frame debugger to confirm the filtering mode at runtime. Step 3. Profile on your target hardware. Capture a frame with RenderDoc or Unity Profiler. Look at texture sampling cost. If your GPU bound and texture sampling is eating more than 20% of your frame time, you have a texture resolution problem, not a filtering mode problem. Downscale first. Step 4. Set a quality gate. If your frame time is under 13 milliseconds on your target device with 8x anisotropic, you're golden. If not, dial back to 4x or 2x. If you're still struggling, disable anisotropic entirely and focus on reducing texture resolution and draw calls. Let me recap the 3 most important takeaways. 1. Texture filtering is how the GPU maps texels to screen pixels when there's no one-to-one relationship. This happens constantly. 2. Bilinear is the baseline, trilinear smooths MIP transitions, and anisotropic filtering handles steep angles. Each step up costs more texture bandwidth, but the visual improvement is often worth it. 3. If anisotropic filtering is killing your performance, your real problem is texture resolution or shader complexity, not the filtering mode itself. Fix the root cause first. If you want a second pair of eyes on your project, we do focused performance audits and training sprints at TheGameDev.Guru. We'll profile your texture usage, identify the bottlenecks, and give you a prioritized list of fixes that actually move the needle. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time!